So welcome back. In the end, we keep the program the way it was. Renato will need some more time at the airport. And I'm very happy to moderate this second session today. The first speaker is Benjamin Knorr from Heidelberg University. And he's going to tell us about perturbative QFT. And let's see what we can learn from this.
Yeah, thank you, Luca. Also, particularly for the invitation and the opportunity to talk to you here about non-perturbative QFT, about some guiding principles, but also about harsh realities that you encounter by trying this endeavor. So Luca gave me specific orders, just to let you know. He told me to focus on the framework of non-perturbative QFT, so this will be the first part of the talk. Giving you my perspective on what we can do in non-perturbative QFT, and maybe what we cannot do, and what we should expect, and what's realistic to expect, in my opinion. And then Luca allowed me gracefully to move on to quantum gravity, as the easy example for non-perturbative QFT. So let's get started, maybe with the question, non-perturbative QFT, where are you going? So I hope that you're all familiar more or less with QFT, but maybe you have to ask, what do you mean by non-perturbative? So you could make a simple statement, right? Non-perturbative is what is not perturbative. Okay, thank you very much. It's maybe not very useful, okay? But even we can ask the question, what do we mean by perturbative? And usually, what we mean in the standard context, if you go to your QFT1 class, it's perturbative in coupling constants, right? You look at the scattering course, or even quantum mechanics, you look at an n-harmonic potential, an harmonic oscillator, x to the 4, and you perturb in the coupling in front of the x to the 4, and compute your energy spectrum or whatever. But this is one specific notion of perturbative. Okay. Maybe let's continue with some typical examples that you might come up with when we talk about non-perturbative physics, and we'll now abbreviate it by NP, non-perturbative. I think a fair answer is whatever happens in QCD, in infrared, is non-perturbative, right? So, very clear example. Instantons, very clear example, I think. It's non-perturbative, certainly in the coupling. We usually have something like an exponential of 1 over the coupling. So certainly not expandable in a series. Now it gets a little bit fuzzy, all order effects. So if you resum your perturbation theory, is that still perturbative? Maybe, maybe not. And one example I really like is the Schwinger effect, right? So you have vacuum fluctuations, electron-positron pair reduction in an electric field. You can compute it at one loop order, but in a background of electric field. So it's one loop, so it's perturbative, but it's not perturbative in the coupling. So is it perturbative or is it not perturbative? You tell me. So clearly, with these examples, defining what non-perturbative is, we have to be very careful, right? It should be more precise what we mean by this. And maybe, ideally, we could define non-perturbative physics as the physics in the full range of the theory, right? So it doesn't matter whether weak coupling, strong coupling, you should understand the theory everywhere. That's maybe the idealistic goal. And now comes the practical viewpoint, right? We have different non-perturbative methods, and they're strong in some aspects, and they're maybe weaker in other aspects. And all of them have advantages and disadvantages. I think it's a good or prudent strategy to use the best tool for the right problem. So maybe in some part of physics you can do perturbation theory, in some other part you do the 1 over n expansion, which is non-perturbative in the coupling, but perturbative in 1 over n, and so on. So let me continue a little bit in setting expectations here about non-perturbative physics in general, but also QFT. So if you want a reality check. So let's start by simple models, simple in quotation marks, right? So think of DFTs, maybe 2 dimensions, supersymmetric theories, So simple in the sense that they're very constrained by their symmetry group. So you can learn a lot about these theories because they have so much symmetry, and you can learn a lot about the non-perturbative region in these theories. But certainly these are very specific theories, and maybe it's not realistic to expect the same level of control in more realistic theories like the standard model or quantum gravity as we have for these theories. So, yeah, let's see. I like as a kind of in-between example, which has real-world applications, but which is also somewhat closer to these really constrained models, is the Ising model in 3 dimensions at criticality. So Wilson-Fisher fixed point, which you can find in nature, right? It's studied to death, right? Any method that you can imagine has been thrown on this model, be it lattice, perturbation theory, large n function methods. And we basically know what this model is, that it exists as a QFT, and nowadays with the conformal bootstrap, it's essentially solved numerically, right? So you can compute critical exponents. So here I give you the relevant critical exponent to right position, enormous dimension, and the subleading critical exponent. You can see, well, this is basically exact for all practical purposes. But once again, let me emphasize that this is highly specialized. Ising model is a very simple model, but maybe a more realistic goal to aim for if you think about non-perturbative physics in a more general context. So ideally, I would like to have some precision like that for quantum gravity, right? That would be amazing. Okay. A few honorable mentions that some interesting ideas I don't know a lot about, but I think that are relevant. One is resurgence. So this is basically the beefed up version of resumming perturbation theory and considering different saddles. And maybe also the left-hand swimmer method as a way to pick a right contour for a path integral. Good. Back to setting expectations. So maybe the factual goal to really formulate it is provable, maybe at least effective control in specific limits for your non-perturbative approach. And in a sense, I would argue that it's back to some kind of perturbative limit. At least this is one way to get control. Not necessarily, once again, perturbative in a coupling constant. Can be perturbative in something else. But if you can constrain your theory from different angles in a perturbative way, maybe you can cover the full theory once again. Thing that I'm very insistent on is I do not think that you will get away without approximations. So take that as a challenge. If you can solve QCD exactly, I invite you for a beer or maybe something more. Okay? But it's my firm belief that eventually you have to do approximations and very likely also numerics. And let me also emphasize that maybe the poster child of non-perturbative QFT, the lattice, is no one-stop shop. Also, the lattice has its disadvantages, like the sign problem from Douglas and so on. There's also an interesting story. Can you ask me privately about it? There are sometimes finite size effects that are setting in later than you expect. So when did we start? 10 minutes ago. Great. So all this, I think, was true in a very general context, but now I'm a quantum gravity person. So you add gravity to that, and of course gravity is gravity doing gravity things, and everything that's more complicated. How can it be different? So the task for the rest of the talk is to take this input and see what happens when I take quantum gravity and try to formulate it as a quantum field theory. So yeah, let's get started with a bare bones story. So I want this talk to be approachable. Of course, there are a lot of technical details that I'm hiding, but feel free to approach me or ask me about these. just a few months ago, or actually I think last year, there was this huge effort, handbook of common gravity, where also this common gravity as QFT, called asymptotic safety, contributed to in these contributions, and you can get it by now for the low price of 991 euros and 75 cents on Amazon. So I keep tracking the price of this book. It's really massive, it's several thousand pages, but it seems to lose value quite quickly, given that it was published not so long ago. But anyway, I think it's a great resource, not only for QFT as a QFT, but QG in general. Let me also briefly advertise that last year we had a really nice more detailed program on quantum gravity, and in the first week we had a PhD school, and the lecture notes are online. And this also covers a whole range of topics on quantum gravity, not only what I'm talking about today. Good. So let's take a step back again. QFT. I think it's an uncontroversial statement that coupling constants in QFT run with energy. Right? So we know that, and have been Nobel Prize for it, for example, for QCD, the strong coupling constant will drop off at high energies. How do we describe that? Theoretically, well, we compute a scattering cross-section and we compare it to the experiment, right? And then we see that we have to identify the constants, quotation marks, and they will just depend on the energy scale of the process. And this whole dependence on energy scale is covered by the renormalization group. Simple example for how we do this is what we call beta functions. So this is the energy derivative, if you want, of the coupling. And in the perturbative expansion in QCD, it looks like this. So it's quadratic, and the prefactor is negative. So you see that you have a negative slope. You decrease your coupling when you go to higher energies. So that's the standard story. QFT1 again, or maybe QFT2. But now you do quantum gravity. You try the standard approach. What fails? Standard renormalization by perturbation theory. We heard a little bit about this, but I would like to go into a little bit more detail here. So you take your Einstein-Hilbert action, so pretty scalar, volume term, and you try. Right? You try perturbation theory, you compute one loop, two loop, and so on. But before you do that, even, you realize something. So power counting tells you that, well, there might be a problem. Right? Newton's coupling has negative mass dimension, and you expect that you run into perturbative non-renormalizability. So what you expect is that you generate more and more counter terms that are not of the form of the Einstein-Hilbert action, with new and new coefficients that you cannot determine in perturbation theory. Of course, there's the whole story about EFT, but I'm now looking from a more fundamental perspective. So the actual problem here is really predictivity. You can do EFT, as I said, but at least in principle, you have infinitely many free parameters if you go to arbitrary high energies. Good, this I already said. So power counting, you expect more and more counter terms at higher and higher loop orders. Surprisingly, at one loop order, GR is fine at one shell. Okay. This is basically a curve of GR because all the terms that you can generate are either topological invariants, which don't really matter that much, or terms that vanish on shell. This phase we've met already, so it's first indication that pure varieties may be a bit special here. But latest at two loops, we've already seen this divergence, you will hit this. Right? So it's I think the Riemann cube or Y cube doesn't really matter. So you hit this term, this will not vanish on shell. So Ritchie flat doesn't tell you anything about the right tensor. And the crucial point, well, this heroic effort in the 80s was already mentioned. So this A tilde, the divergence, does not vanish. So you generate this term at two loop orders, and then you kind of think about it a little bit, what you could generate at three orders, four loop orders, and so on. And you realize that likely the power counting argument or idea is realized, and you get more and more free parameters to higher loop order. So from this, we usually conclude that GR is perturbatively non-renormalizable. And here, let me stress perturbatively non-renormalizable. So let me maybe rephrase this. You can make a question out of it: is gravity or GR non-perturbatively renormalizable? Right? Are we connecting to the story of the talk, non-perturbative QFT? So this is a question that you can ask, and I think we have some partial answer on this. And this whole thing goes under the name of asymptotic safety. So the hypothesis of asymptotic safety is that metric gravity, as we know it, classical matter, think of the standard model, maybe some dark matter, can be formulated as a QFT, but you need non-perturbative physics to do that. What's the idea? Well, let's come back to the renormalization group, right? So we already had the example of asymptotic freedom, so couplings go to zero at very high energies, and then you can do perturbation theory. That's not the only way that you can make sense out of a QFT. The other way is asymptotic safety, so this is the orange line, where your coupling doesn't go to zero, but approaches a finite constant at very high energies. And this has to happen for all couplings in your theory. To be a bit more precise, there are really two conditions here. The first one is that the couplings have to approach a finite value at high energies, which we call a fixed point of the RG flow. And the second one is solving the predictivity issue, right? So just having this fixed point is not really enough, because you could still maybe fear or hope or whatever that, well, maybe you need infinitely many couplings and you still have infinitely many parameters, and then you haven't really improved the situation. So the second is that in a technical sense, you only need finitely many relevant operators, which means that the RG flow, or this fixed point, has to fix an infinite number of couplings in terms of a finite number of couplings that you fix by experiment. So these conditions really, in a nutshell, are finiteness, of scattering amplitudes, and predictivity. What is enabling this asymptotic safety from a physics perspective is a new symmetry. We already heard about it a little bit yesterday in the poster flash presentations, and that's scale symmetry at very high energies. Right? So beta functions vanish, that's scale symmetry. Good. So this is the kind of physics picture, or like the idea that we want to investigate or test. So how do we do that? What's a good non-perturbative method that you can throw at this idea and see whether it works? And you can do this with lattice, but I'm mostly working with the so-called functional renormalization group that I'll briefly discuss now. So what is this? This functional renormalization group, or FRG, is based on the Wilsonian idea of integrating out modes shell by shell. So you don't do the path integral in one fell swoop, but you kind of chop it up into momentum modes, and then you integrate out a little bit, until you've integrated out everything. That's the kind of intuitive picture. So in a plot, you start with your microscopic action, S, that is the one that is in the path integral, and you want to compute the effective action that you know from QFT in some way. And what the FRG does for you is it defines essentially an interpolation, so we call it effective average action, gamma k, which is a one-parameter family of actions that at very high k goes to this classical or microscopic action, and then for k to 0 gives you the standard effective action. So if you would have that, it would be really nice. And it turns out that there is an equation for this interpolation function, or functional. It's called the Wettreich equation. The exact form doesn't really matter. The important bit is that you have a k derivative on the left-hand side for this gamma k, so it's the first differential equation in this coupling k, in this scale k, and then the right-hand side is essentially a beefed up one-loop diagram. The key point about this equation is that formally it's exact, which also means it's non-perturbative. Okay? So if you do not make any approximations, and you would be able to solve this equation, you can compute the effective action given some microscopic action. But now, both of you knows what the no free lunch theorem is? The no free lunch theorem is there's no free lunch, right? I already told you that. I think that you cannot get around making approximations, and of course, like every non-perturbative tool, we have to make template. Okay, we have to make approximations also here. But now there's also, unfortunately, no free dinner. At least the standard implementation, and I'll come back to that, that's why they asked for it. Standard implementation, most of the literature is connected to Euclidean signature, but there's been some progress on this lately. Good, so you have this formally exact equation. You can ask, does it work? Right? And maybe you do not want to start with quantum gravity, where things are anyway a little bit unclear, and you might want to step back maybe to the Ising model or simple models and ask, well, you've written down this equation, it's horribly complicated, does it work? Does it give comparable results to the lattice, to perturbative theory, to whatever? And there's 30 plus years of work on using the FRG on all kinds of models. Condensed matter, really any flavor of Ising model or N model or Snowball model, you name it. Any type of scalar theory or fermionic theory has been computed to death. QZD, very nice results. Competing with the lattice. In some parts of the parameter space, this tool does not have issues of finite density and temperature. So there are clearly parts of the phase space or phase space of QCD where FRG works better than the lattice, or more easily. And there's a lot of other things that I don't know that much about, but certainly you can do non-equilibrium physics, turbulence, multi-scale physics, you name it. So if you have any kind of statistical physics or QFT that is not gravity, has been investigated. There's a really nice review from a few years ago where there's basically references to any of these models if you want to have a look. But now let me maybe be a bit more quantitative. I told you that from the conformal bootstrap we get, for the Ising model, this numerical computation for the critical exponent. And to compare to that, the best that we have right now with the FRG is this way. You see that basically the 4 first significant digits are spot on. And this was given 6 years ago. So if you want to try, you can definitely improve on this, but this is just to say that this thing works, and we've tested it. People have tested it in all kinds of theories. So a priori, there's maybe no reason to doubt that it might not work for gravity. So you have to just throw it on quantum gravity and see what comes out. Okay. Good. So let me advertise a little bit what we found in asymptotic safety. So what's the status? First computation maybe, you can find that out in '96 by Martin Walter. Very simple approximation, right? You take the ancient Hilbert action, you throw it into this equation and see what you get out in terms of beta functions. It's a pretty harsh approximation, but in this harsh approximation you find a fixed point. Okay. So, could have been different, but this is what comes out. Of course, '96 is almost 30 years ago, and since then hundreds of papers have been written on this topic with more and more advanced approximations to this equation. All of them find a fixed point, find the fixed point, so we are pretty sure that it's the same fixed point. Not everything goes, so we've coupled matter to gravity, there are bounds on them, certain matter affects the fixed point different than other matter. For example, Vector fields seem to be harmless. They make the fixed point a bit more perturbative, but scalars are maybe a bit more tricky. So there might be bounds on how many scalars you can couple so that the theory is still asymptotically safe. But the standard model falls into the safe regime. I also have some quantitative results. So within asymptotic safety and also again within approximations, we can get the right mass ratio of Higgs to 12. I think this is impressive. It could have been different, right? I could dream up a quantum gravity theory. Everything works formally, it's unitary, whatever you tell me. And I compute the Higgs mass and the top mass, take the ratio, and it's the wrong number. So you have the best theory, but it's not describing reality. And here, at least, there are some hints that you're not too far, right? So the measured value lies within our range right now. You can wonder how many free parameters we are adding in the gravitational sector on top of the standard model. And we seem to converge to 3. That's the cosmological constant, Newton coupling, and an R-squared coupling, roughly. So with 3 additional parameters on top of the standard model, it seems that we have fixed the theory. Some more property, I already told you that most of the computations are Euclidean. Like 2 or 3 years ago, people started to investigate Lorentzian flows, and kind of the upshot is there are no big surprises. It seems to be stable. People have computed spectral functions of the graviton. No surprises there. We do not have additional poles, no ghost poles, no other poles, and there are strong indications for unitarity. So this theory seems really to be the minimal extension that you would hope for if you start out with GR and want to quantize it. There's no additional garbage, it's just kind of the maximally boring scenario. Right? So you have the kind of EFT regime at low energies, you have a transition roughly at the Planck scale to the fixed point scaling, and then there's fixed point scaling. This is kind of the very simple picture. Of course, there are more details and more subtleties, but I think the big picture is roughly this. And to give you just one illustration of this point, is that 52 or 7? Just for one illustration, what we can do, let me come back to the two-loop counter term. Right? So they generate a perturbation theory at two-loop order, and you can ask the question, what does asymptotic safety do with this term? Does it destroy it or not? So you make an ansatz for this effective average action of roughly this form. I'm hiding a lot of details now, you can ask me later about this, but I certainly add this Gaussian-Neutrino counter term. Now you ask, you compute the beta functions of lambda g and this YQ coupling, and you ask, is this term relevant or irrelevant? Right? So do I have to measure it, or is it fixed by the theory? And it turns out it's fixed by the theory. So what you see here is a phase diagram. So these are the integral curves of the beta functions. And what you see here in the center is the UV fixed point. So this is high energies. And you see there's only 2 lines going out of it, up, and then this ends in a singularity, or down. So basically in this approximation, there's a unique theory that is asymptotically safe at high energies and gives you a standard EFT of GR at low energies. And the single line, that means one parameter of the 2, so Newton coupling and this Gaussian-Neutrino coupling, is fixed in terms of the other. Great. So asymptotic safety tames two-loop counter term. They are strictly better than perturbation theory. And the general expectation is, and there's also a lot of work on this, that even higher order terms that you can think about, like R to the 500 or whatever, is much more irrelevant. So it's also predicted by the theory. Good, but now maybe end of the advertisement. Of course, there's also some harsh reality. And I think it's not fair to only present the good stuff, but also to be honest and point out where we maybe still have questions or issues where we can improve. So it's certainly not the full story yet. So some issues, the first issue is a little bit systematic error control. We're working on this, but so we have a non-perturbative method. It's intrinsically more complicated to give reliable error estimates, but we're working on it. A few issues with the homomorphism errors, that's maybe a bit more technical point, let me skip that. Lorentzian signature, I already told you a little bit about. Certainly first very good steps. It's also, of course, crucial if you want to make the step to scattering amplitudes, because Euclidean scattering is a bit strange, right? If you think of a graviton external line, that's on shell. On shell means p squared is 0, but in Euclidean signature, p squared is 0 means you don't really have anything propagating because p is 0. So for that, for external graviton lines, you really need Lorentzian signature. There's a whole big question about landscape and swampland connections there, unitarity bounds, positivity bounds, and in general the connection to EFT. So, I told you that there are some indications that we have a unitary theory, but so far there's no proof. It's just that we can say that with reasonable confidence that we do not see any additional poles. That does not mean that the theory is unitary. It's something that we have to prove. And then things like how do quantum black holes look like in this theory? Right? For that, we would have to derive the equation of motion from the effective action and solve them. It's a very hard problem, but also there are a few movements. Let me at this point also point out that a few years ago, John wrote a critique of the asymptotic safety program, and 1 year later, there was the critical reflections from inside of the community, and both of them are really were excellent for the field. So you could think of, well, criticizing your program, that's maybe not so nice, but really this initiated a lot of momentum and really trying to, on the one hand, explain things better, but also tackle issues, right? So this was really valuable for the field, and it caused a lot of progress. As I tried to point out, there's work on all of these issues. I think this is where really the progress is happening right now, the fastest. So these are the issues, but there are also issues, right? So maybe the more complicated issues, where I don't know, or I don't have good ideas, or maybe it's a bit more critical. There's been some work on more mathematically rigorous treatment. It's also connected to Lorentzian signature, how you define properly the propagator, and things like that. How do you really sum configurations in a Lorentzian signature in contrast to Euclidean signature. One thing that I stumbled over just recently, so there's a very recent paper, IR non-localities might be an issue. So it turns out that the LSZ formula breaks down if you have long-range forces, because asymptotic states are not really free if you have long-range forces. So at least in my opinion, there's something there. If you know more about this, I'm very happy to talk to you. And then maybe once again, the whole connection to the swampland, to black hole ideas, black hole thermodynamics, topology change. And let me just very briefly advertise, we had a nice work recently, a few months ago, Alessia, Ivan Vasile, and Mark Scheffer, where we tried to investigate the connection of asymptotic safety and the swampland ideas. And maybe the upshot is that if you follow the standard law of black hole thermodynamics, black hole physics in an EFT framework, this is remarkably constraining. And there might be some strong constraints and with the black hole physics on one hand and asymptotic safety on the other. But now I'm in a fortunate position that there is one co-author also in the audience, so you can ask Alessia about. Good, so let me wrap up. I think it's fair to say that non-perturbative physics is hard. Maybe to define really what non-perturbative physics is, you have to define what you not want it to be. So what's it perturbative in, what is it non-perturbative in? Surprisingly, if you apply non-perturbative physics, or RT or whatever, on quantum gravity, it's surprisingly resistant. So we really have not found a way to get rid of this fixed point. It's extremely stable. So something is there. But it could, of course, still turn out to be not unitary, not causal, whatever. There might be issues with it, but as a fixed point, I'm pretty sure it exists. Controversy is good. As I said, asymptotic safety works practically. There might be some challenges, especially with black hole physics, but as we had heard yesterday, controversy is good. I think there are some big opportunities. Let me emphasize again that taking criticism seriously and also cross-field collaboration is what brings the field forward. With that, I thank you for your attention.
Thank you, Benjamin. We have time for one question, and then we move the remaining question to the afternoon, okay?
Question, thank you. So I just wanted to ask your opinion about this recent work on adding a measure to the functional integral that apparently destroys the Reuter fixed point. That measure, I believe, is something like that needs to be there, and I'm just curious about if it destroys the Reuter fixed point, is it going to destroy lots of fixed points?
Yeah, so you're referring to the work by Campagna and collaborators. Yeah. Well, there's a reply, and
there's a reply to the reply.
Yeah, exactly. Let's say I stand by the reply. I don't think that they really have a reasonable RG flow or what they've written down. In any case, what they look at is a one-loop flow, and a one-loop flow is not an argument against the existence of a fixed point.
But it's something that did work. Doing that without the measure term did work, and doing it with it doesn't. But yeah.
Yeah. So
that's your answer. Okay.
Yeah, I think that the yeah, I think there are arguments why this measure that they're using is not working. At least from that's my perspective.
Yeah, I think this could also be one of the topics of the discussion.
Sure. That's the other reply, yeah.
So, okay, let's thank Benjamin again.